Hi, my name is Akin Yokuno. I am from the Institute of Statistical Mathematics, and I'm also a visiting scientist of Riken Center for Advanced Intelligence Project. Today, I'm going to talk about the optimal nonparametric classification via radial distance. This work is joint work with Luigi Gao, Kei Nakagawa, and Hidetoshi Modaira. Mr. Kao was a master student in Shimodaira Laboratory in Kyoto University when I was a doctoral student, and Dr. Nakagawa is a researcher in Nomura Asset Management, and Professor Shimodaira is a professor of Kyoto University. He was a supervisor of mine when I was a doctoral student. Okay, anyway, I talk about this topic. At first, I'd like to talk about the related publications of ours. So in English, we have already published 2 manuscripts. The first manuscript has been published in the New Lips 2020. This study considers the multi-scale variant of the K-nearest neighbor estimator. And the second manuscript focuses on the local radial regression, and this manuscript focuses on the application to the prediction of the stock prices. So these 2 manuscripts are written in English. And also we have published these 2 manuscripts written in Japanese. These manuscripts are published in the annual proceedings of the Japanese Society for Artificial Intelligence. Okay, so anyway, these 4 papers are related to this study. At first, I'd like to describe the background of this study. Okay, in this study, we consider the regression and classification problems. Okay, I'd like to discuss about the regression problem. Okay, here, X and Y represents a pair of covariate and its response variable. And then usually the regression problem estimates the regression function fx, which is defined as the conditional expectation of the response variable y is given the fixed covariate x. So the conditional expectation is denoted as the function fx, and then we want to estimate this function fx by using some regression functions. Usually, for the classical and standard regression problem, we employ the linear regression model or neural network or something like that. So actually, if we obtain the observations x and y, usually we estimate some linear regression model, which is defined as the linear model with respect to the input x, or we sometimes employ the neural network, which is defined as the nonlinear extension of the linear regression model. Okay, so usually we employ these types of regression models, but in this study we consider somewhat different problems. In real-world situations, sometimes several different forms of covariates are mixed. So as you can see, in this linear regression and neural network, we usually assume that the vector x has the same dimensionality, but sometimes in real-world situations, the dimension of the data vectors can be different. So in these special settings, the typical regression functions like a linear regression model and neural network, which is also called a perceptron, cannot be applied to these types of, different lengths of data set, different dimension of data sets. Okay, so from here, I'd like to explain some examples of these special settings. Okay, so as a first example, I'd like to show a mixture of pictures, drawings, and text. So in this example, we obtain several data sets, and each data set is classified into either pictures or drawings or text. So for instance, the data set X1 represents the drawing of the chimpanzee. And also, as you can see, the data vector X2 represents a drawing of gorilla, and also the X3 represents the text of chimpanzee. And then actually, so these datasets have different, so these datasets are different in the different forms. So usually the dimension of data vectors can be different depending on the data type. But as you can see, we can sometimes measure the similarity or difference between these data vectors. So for instance, this image of gorilla and this drawing of gorilla should be close in terms of some difference or similarity measure. But the image of gorilla should be distant from the text of giraffe compared to the drawing of gorilla. So we can formally define some distances or some similarities even for these types of data sets. So then we want to estimate whether some object represents the primates or some not primates or not by using these types of data sets. So this is a kind of, to say, extended setting of the regression problem. So this is the first example. And also we show the second example in this slide. In this example, we consider the time series of the different lengths. So for instance, in this study, we consider the record of the stock prices in each month. And as you can see, each month includes the different number of days. So for instance, the February usually includes the 28 days, but the April consists of maybe 30 days, right? So the number of days can be different depending on the month to be considered. So the record of the stock prices can have different dimension depending on the month. So we employ the stock price record in each month as the data vector xi, but actually the dimension of this data vector can be different depending on the month. So this is a kind of the different dimension of data vectors, and then we want to estimate whether the price increases or not, or decreases. So the predicting whether the stock price increases after the month from the stock price record in each month can be regarded as as a practical example of this problem setting. So these two are the practical examples of the problem setting considered in this study. Okay, so even for these types of data sets, we can employ several existing estimators. So for instance, the distance-based approaches can be applied to these types of data sets. So from here, I'd like to explain about the kernel smoother, which is a standard method in the field of nonparametric statistics. In this method, we usually first seek the data observations xi, which is close to the query x. So we want to estimate, to predict the level of this query x. And then at first, we first seek several observations whose distance to the query x is less than h. So then using this set, then we just simply take an average of the labels whose covariance is close to the query x. So this is called the kernel smoother. And usually the kernel smoother employs, I have to say, mathematically rigorous distances, but we can formally replace this distance to the similarity or dissimilarity measure, which is defined for these types of mixture of datasets. So then we can formally compute the kernel smoother estimator by using, to say, the extended distances or extended similarities. So we can apply these types of distance-based approaches to the different dimension of data vectors. And and also for instance, for the second example, we can employ the several metrics like dynamic time mapping to measure the different lengths of time series. So dynamic time mapping is defined for the different lengths of time to measure the time series who have different lengths. So then we can formally calculate the kernel smoother even for the different lengths of time series or something like that. So we can say that the distance-based approaches are formally widely applicable by leveraging the extended version of similarity or distance measures. So, and also the kernel smoother with K is also called K nearest neighbor estimator. So K nearest neighbor estimator is very similar to the kernel smoother. Anyway. Okay, so I'd like to explain about the conventional theory for the kernel smoother and some nonparametric estimators. So here consider a case that the data vector has the same dimension for simplicity, and then in the classical theories, the kernel smoother and kernel neighbor are consistent, meaning that the estimator converges in probability to the underlying true function. But even if these estimators are consistent, they are known to be not minimax optimal if the underlying function is highly smooth. So for instance, if the true function is if it has a second order derivative, then actually these estimators are not optimal estimator. So the conventional local polynomial estimator or some other estimators correct the asymptotic biases of these estimators. So as a summary, the kernel smooth and kernel neighbor estimator are widely applicable. So these estimators can be computed even for the different dimension of data vectors, but they are not optimal. And on the other hand, the local polynomial regression estimator is not widely applicable, but actually this one is optimal. But the local polynomial regression estimator cannot be computed for a different dimension of the data vectors because it needs, how to say, some more additional information other than the distance or similarity measures. So the problem here is that can we correct the asymptotic bias while holding applicability? So this is a problem considered in this study. Okay, from here I'd like to discuss about the proposals. Okay, as an overview, in this study we propose two estimators. The first estimator is called the multi-scale k-nearest neighbor estimator, which corrects the bias of the conventional k-nearest neighbor estimator. And also we propose a local radial regression estimator, which corrects the bias of the kernel smoother. So the local radial regression uses the different type of generalization from the local polynomial regression. So yes, so we propose these two estimators. Okay, I'd like to explain about these two estimators briefly. The first estimator is called multi-scale k-nearest neighbor estimator, which was proposed in the NeurIPS 2020. So the idea of this estimator is very simple. To calculate this estimator, we first compute the several k-nearest neighbor estimators for different cases. So for instance, at first we compute the k-nearest estimator for k equals 100, 200, 300, and 400, or something like that. And after that, we conduct some regression analysis to extrapolate these k-nearest estimator from the different k's to k equals 0. Then actually, we can obtain the imaginary zero nearest neighbor estimator by using this extrapolation. So the extrapolated value is called the multi-scale k-nearest neighbor estimator. And actually, this estimator can reduce the asymptotic bias without increasing the asymptotic variance. So actually, this estimator can be computed only from the distance. So this estimator also can be applied to the different dimension of data vectors. So I mean, the multi-scale k-nearest estimator is widely applicable. And actually, this one can be minimax optimal. So this estimator can have these two favorable properties simultaneously. And also, we define the local radial regression estimator. So this estimator is very similar to the multi-scale k-nearest estimator, but actually this one is a variant of the multi-scale k-nearest estimator to the kernel smoother. Yes, and also this estimator is also minimax optimal and widely applicable. Okay, so these two estimators are the proposals. So in this, as a theory, we can prove some good properties of the multi-scale k-nearest estimator and local radial regression estimator. So yes, so for instance, the multi-layer perceptron, which is also known as the neural network, is limited to, it cannot be applied to the wide range of datasets. And also, actually, this one is not optimal for in the sense of higher order optimality. but kernel smoother and k-nearest neighbor estimator can be applicable, but they have not optimal in the sense of higher order optimality. Local regression is not applicable, but yeah, these two estimators have these two favorable properties. So this is the theories. Okay, anyway, we want to describe about the experiments from here. Okay, in this experiment, we first examine the result of the multi-scale k-nearest neighbor estimators. So in this experiment, we employed several datasets collected from the UCI machine learning repository, and then we computed the multi-scale k-nearest estimator and k-nearest neighbor estimator to predict the level. Yeah, and then as you can see, the bold characters represent the best score, and then you can see that the multi-scale k-nearest neighbor estimator overall have a tendency to, to outperform the k-nearest neighbor estimators. So this is a simple result. Okay, and also we applied the proposed methods to the stock prediction problem. Okay, so in this experiment, we first collected the record of the stock prices in each month. So for instance, we collected the stock prices of the S&P 500, TSX, Euro, or something like that. So yeah, as I explained earlier, the XI represents the stock price record in each month. So actually, this vector has the dimension of this vector is the days in each month. So the dimension of these vectors can be different depending on the month. And yi represents whether the stock price increases or decreases after this month I. So we want to predict whether the price increases or not from the stock price record in each month. So then we can regard the stock price prediction problem as a regression or classification problem. So in this example, we conduct several simulations, computational simulations, and then we determine whether we buy or sell some stocks by using this classification result. So then the cumulative return, we computed the cumulative return in this simulation. And as you can see in the red line represents the result of the proposed estimator local radial regression. So as you can see, the proposed method demonstrate the better cumulative return compared with other estimators. So this is the experimental results. Okay, so this one shows the predictive classification accuracy. And as you can see, the best score, which is emphasized as bolded letters, bolded characters, as you can see, these two estimators outperform the random prediction and the k-nearest neighbor estimator, or something like that. So this is our results. Okay, here I'd like to conclude this talk. Okay, in this talk, we consider the kernel smoother k-nearest neighbor estimator. Yeah, and actually these two conventional estimators are widely applicable because these estimators can be computed or even for the different dimension of data vectors. But they are not optimal when we estimate the highly smooth functions. But on the other hand, the local polynomial regression, which corrects the asymptotic bias of the kernel smoother, is minimax optimal. But actually, this estimator is not widely applicable to the different dimension of data vectors. So to obtain these two favorable properties, simultaneously we proposed a multi-scale k-nearest neighbor estimator and local radial regression estimator. So, yeah, so these estimators have these two properties simultaneously. Yeah, so we propose a widely applicable and optimal estimators. And also this study is mainly based on our new LIPS paper, okuno-lab Shimodaira, LIPS 2020, and the archive paper, so okuno-lab Shimodaira. Okay, so these are the conclusion of this talk. So if you have any question, please feel free to get in touch with me. Okay, anyway, thank you very much for listening.